Unit 10 is basically Unit 10 is basically redox titration, and these titrations are based on type of oxidation and reduction reactions. We'll go one by one. First of all, what do we mean by redox reaction? Then what are the objective of redox reactions? How do I identify a reaction is reduction and oxidation both or not? Then we'll discuss about the reactions in two half cell reactions called oxidation half cell and reduction half cell. Then we'll go to redox potential. Then we'll go to electrochemical cell. In electrochemical cell, we'll discuss the Nernst equation and also calculate the EMF of the cell called cell potential. Then we'll discuss about the equilibrium constant and how the equilibrium constant is related to cell potential. We'll also discuss about redox titration and redox indicators. Then also we'll discuss about the application of redox titration, then oxidimetric reagents, reductometric reagents. So these are our topic of discussion for today's class. So we'll discuss one by one now. First of all, about the introduction part. And in introduction part, remember one more thing, one thing very important. That is, what do you mean by reduction and what do you mean by oxidation? So remember, students, in any chemical reaction, in any chemical reaction, for example, the reaction, in any chemical reaction, like you can say that loss of electron takes place or electron loss occurs, then it is called as oxidation reaction. And if gain of electron occurs, it is called reduction reaction. So loss or gain of electron can be, you can also visualize through increase or decrease in oxidation number. For example, it is Fe loss of electron means Fe minus 2E. E means electron, small e. Then it gives rise to Fe2 plus. So Fe minus 2E gives rise to Fe2 plus. So here you see Fe has 0 oxidation state and Fe2 plus has plus 2 oxidation state. So there is an increase in oxidation number 2. So when there is an increase in oxidation number by 2, the reaction is called as oxidation. So increase in oxidation number is called oxidation, or you can say loss of electron is also called as oxidation. Similarly, decrease in oxidation number, let it be Na plus E. Na plus E means minus 1 charge. So Na has plus 1 and plus E means minus 1. So plus 1 minus 1 cancels. So Na plus E gives rise to Na. So here you see that plus 1 oxidation state becomes your 0 oxidation state when it becomes NO. So Na plus to Na is a decrease in oxidation number or gain of electron. We call it a reduction. So now it is clear that what is reduction, what is oxidation. So okay, then now we'll discuss this part. So reduction means Fe2 plus to Fe3 plus is oxidation, and Cl2 to Cl2 minus. You list your Cl2 to Cl minus. So Cl2 plus 2E, it gives rise to 2Cl minus. You can refer to the unit number 10, and your point number is 10.2. 10.1 is introduction, the syllabus, what we are going to read, and 10.2 is the redox reaction and redox potential. Okay, reduction potential. So look at this. Fe2 plus Fe2 plus is oxidation. Similarly, Fe2 plus to Fe3 plus is also oxidation. So loss of electron is oxidation. gain of electron is reduction. So when both occur simultaneously, we can say it is a redox reaction. So redox reaction means oxidation and reduction always found together in a reaction. Such reactions are called redox reactions and are also called electron transfer reactions, because in one case electron is lost and in second case electron is gained. So loss and gain both occur in the same reaction, hence it is called a redox reaction. Hence it is called the redox reaction. So redox reaction means gain and loss both occur in the same reaction. Then come to redox reaction as two half cells. Redox reaction as two half cells. So remember, when oxidation takes place, we call it oxidation half cell, called loss of electron. When reduction takes place, we call it reduction half cell, or called as the reduction simply. So there are two half cells. One is oxidation half cell, one is reduction half cell. And when both you add, then you get the net cell reaction. So net cell reaction will be simply the addition of two half cells. One is oxidation half cell and second is a reduction half cell. Okay. Then one more thing you remember here, that if 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 any species undergoes a reduction, then itself is oxidizing agent. Any species undergoes a reduction is itself an oxidizing process. Any species you are thinking is undergo reduction, then it is an oxidizing process. Similarly, if any species itself undergoes oxidation, then we can call that substance is said to be an reducing agent. So species which undergoes reduction is oxidizing agent. The species which undergoes oxidation is called as the reducing agent. So reverse one. A reducing agent means oxidation takes place. Oxidizing agent means reduction takes place. Okay. So now I think students, you are clear about redox reaction. Any doubt you can ask me now. No doubt. Redox reaction, any doubt? Okay. Okay, we will proceed further. Next is redox potential. If a system contains both oxidizing agent and its reducing product, then there will be equilibrium between them and the electron. If an inert electrode like platinum is placed in such a redox system, for example, one containing Fe3 and one containing Fe2 ion, it will assume a definite potential indicative of the position of equilibrium. If the system tends to act as an oxidizing agent, it will take electron from platinum, leaving the latter positively charged. On the other hand, if the system has reducing properties, that is, electrons will be given to the metal, which will acquire a negative charge, the magnitude and spin of potential of an platinum electrode will thus be a measure of the oxidizing and reducing property of the system. So remember one more thing here. In always a particular reaction, there will be an oxidizing agent, there will be a reducing agent. When an oxidizing agent combines with a reducing agent, then you get another reducing agent and another oxidizing agent. So oxidizing agent becomes a reducing one, and reducing agent becomes an oxidizing one. Then there will be a change in potential called as redox potential. Redox potential is a quantitative characteristics of the oxidizing or reducing power of a reagent. So now take an example to explain what is called redox potential. 1 minute. So reduction potential, to know its significance, consider a cell PT H2 slash H plus A equal to 1 means activity of when a concentration A is equal to 1, and then again you have Fe3 plus or Fe2 plus A is equal to 1 and then PT. So here the potential measurement in this way is called a standard reduction potential, reduction potential, because here you have both plus 3 and plus 2. Plus 3 to plus 2 is reduction, but plus 2 to plus 3 is called as oxidation. So here the two half cells are, one is F2 plus, so here you see the two half cells are given here. So remember, in a cell notation, a single vertical line indicates solid liquid interface. A double vertical line represents a salt bridge. So if you find a single line drawn, perpendicular line drawn, it is called as the solid liquid interface. But when a double line is drawn, it is called as a salt bridge. So similarly, you can see here PTH2 slash H plus. So it is a liquid and gas interface. But when it is a double arrow, then it is called as the salt bridge. Then again you see Fe3 plus, Fe2 plus, and then PT. This is all about here a standard redox cell written in this form. Okay. So similarly, each redox cell has a potential. So then the potentials are given in the table 10.1. There you can see that many reactions are given and their potentials are also given. A negative value means that the redox couple is a larger reducing agent. If the value is more negative, for example, you see lithium has minus 3.04 volt. It is a E0 value, so it is written in volt. The potential is in volt. So as per the rule, if the redox couple is a stronger reducing agent, while having a negative value, a stronger reducing agent means lithium plus is a stronger reducing agent. Whereas the positive value means that the redox couple is a weaker reducing agent than hydrogen. All these values are compared with respect to hydrogen. All these values are compared with respect to hydrogen. Remember, all these values are compared with respect to hydrogen. So you can see that you can see that the values are given. First value is for fluorine. So fluorine is a very good oxidizing agent. Fluorine is very good oxidizing agent, whereas lithium is very good reducing agent. So fluorine is very good oxidizing agent. Lithium is a very good reducing agent. It depends on, then it is a good reducing agent as compared to hydrogen, and zero is positive, then it is a it is a very good oxidizing agent. So F2 is very good oxidizing agent, whereas uh, the lithium or sodium or alkali metals, they have very good reducing agents. This is you can find in the redox couple written in the table. Thus, redox potential enable us to predict which ion will oxidize or reduce other ion at unit activity or unit molar concentration. This A is equal to 1 means, remember, it is unit activity. The most powerful oxidizing agent are those which are at the upper end of the table. So, as I have told you, in the table, fluorine tops the list. So, fluorine is a very good oxidizing agent. Which one tops the list is a very good oxidizing agent. And similarly, the most powerful reducing agents are at the end. So the most powerful reducing agent is at the end of the table. For example, the standard reduction potential of cerium is highly positive. Cerium Ce is highly positive. That is the reduction of cerium IV ion is quite spontaneous. So cerium 4 acts as a strong oxidizing agent. So those which is high value of E0 is strong oxidizing agent. So cerium 4 is strong oxidizing agent. Other in the other case you see zinc is value is negative. You know zinc 2 plus by zinc E0 value is minus 0.76 volt. You can see the table also, minus 0.76 volt. So I can say that this minus 0.76 volt indicate that it is a good what here means it is a good oxidize reducing agent. It is a good reducing agent. So but remember is a meaning that there, for example, zinc 2 is a weak oxidizing agent and is a strong reducing agent. Similarly, you can look into any standard redox systems like MnO4 minus 2, Mn2 plus. Here you see MnO4 minus plus 8H plus 5 electron is Mn2 plus 4H2. So here the manganate ion now becomes Mn2 plus. So MnO4 minus becomes Mn2 plus. So you see here that manganese in plus 7 oxidation state becomes Mn plus 2 oxidation state. So in this case, you see it is a reduction. Manganese plus 7 to manganese plus 2 is reduced reduction because decrease in oxidation number is called as the reduction. So manganese 2 plus is reduced, manganese 7 plus is reduced to manganese 2 plus. Manganese 7 plus reduced to manganese 2 plus. So this is a reduction. So Mn2 plus for 47 is an oxidizing agent. As you know, MnO4 minus is a very good oxidizing agent. And also the value clearly says that it is an oxidizing agent because of its positive value of reduction potential. So from this we conclude that uh, reduction or oxidation or redox reactions and their potential, and the potentials are measured in terms of electron in volt, sorry, a potential in volt, E0 in volt, and we have seen now a table is given in 10.1 where all the redox couples, their potentials are given. From that you can ascertain which one is a good reducing agent and which one is a good oxidizing agent. Okay, then we go to next thing, 10.3, electrochemical cell. Next we go to which cell? Electrochemical cell. So here two important things. First of all, what do you mean by electrochemical cell? If somebody will ask, See, the direct transfer of electrons from electron donor to electron acceptor in a redox reaction can be best illustrated in immersing a piece of zinc in a copper 2 sulfate solution. It is observed that copper is deposited on the surface of the metal, means a piece of zinc is dipped in copper sulfate solution. It is seen that zinc is deposited, that the copper is deposited on the surface of the metal. The copper ions migrate to zinc electrode and get reduced, thereby extracting electron from it. The zinc metal dissolves and generates zinc 2 plus ion in solution. It is important to mention here that such a transfer of electron can still be accomplished even when the electron donor and acceptors are away from each other. This can be achieved in an electrochemical cell. So listen first of all, what is electrochemical cell? You dip zinc in zinc sulfate solution in a beaker. Zinc is the electrode here, and zinc sulfate is the electrolyte. Yes, yes. Hello. Any question? Hello? No. Electrochemical cell. So here, two beakers you take. In one beaker, you take zinc sulfate and put zinc electrode. In second beaker, you take copper sulfate and dip copper electrode. Both the electrodes are joined to voltmeter and there is a salt bridge in between. So two solutions are connected through a salt bridge. Zinc is oxidized means zinc becomes zinc 2 plus ion. So the electrode zinc becomes thinner and thinner because from the electrode also, because of loss of electron, zinc is ionized to zinc 2 plus and comes into solution. Similarly, the electron so lost by zinc is now carried by using galvanic cell. So galvanic cell means a particular cell in which the redox reaction takes place. The redox reaction takes place not in one beaker but in two separate beakers. And here the salt bridge contains inert electrolyte like potassium nitrate in agoro-agoro gel. Agoro-agoro gel. In agoro, you add agoro-agoro gel, potassium nitrate, make a paste of it, and then you take in this U-shaped tube called as the which called as the U-shaped tube called as 1 minute. Wait for a minute. Okay, so here the Salt bridge contains potassium nitrate solution along with agar gel, and uh, such as such as electrolyte is called inner electrolyte, and external circuit is maintained when you are using the salt bridge. Without salt bridge, it is not possible to maintain the electrical neutrality. And here the reaction is zinc 2 plus and copper 2 plus to copper. Remember, very difficult thing, or you can say very important thing. Zinc 2 plus. First, this will happen, and then copper 2 plus to copper. So zinc is oxidized to zinc 2 plus, whereas the copper 2 plus is oxidized to copper. So the net reaction is zinc minus 2 electron, zinc 2 plus, and copper 2 plus plus 2 electron copper. You can cancel electron, both the electron you can cancel. So zinc plus copper 2 plus becomes copper 2 plus zinc. So zinc plus copper 2 plus becomes copper 2 plus zinc. This is the net cell reaction. It is also called as the galvanic cell. So a cell, so you can say it is called the voltage produced by electrochemical cell is directly related to the equilibrium constant for the particular oxidation and reduction process. Therefore, Nernst equation is used to calculate the electromotive force or EMF of the cell. So Nernst equation is important. It is used to calculate Nernst equation is used to calculate the EMF of the cell. So we'll discuss this how to calculate EMF of the cell by using a Nernst equation. So what is Nernst equation? I'll discuss it. First of all, consider a redox reaction. Redox reaction means a reduction half cell. You know reduction half cell means what? Copper 2 plus 2 electron, it becomes copper. So in this case, I have not taken copper, or and I will take any metal M. So Mn plus means M is the metal, N plus is the charge or metal ion. Like copper 2 plus, so M is the copper, and N plus is the 2 plus. So Mn plus N electron becomes your M. So remember, Mn plus is the ion, hence it exists in aqueous solution. But M is the solid, so in solid state. So it is an equilibrium between metal ion and its solid. So Mn plus aqueous plus N electron becomes M. This is your reduction half cell reduction. So now when you do the reactions, when you consider this, that the EMF of the cell is Emn plus by M. So Emn plus by M is equal to E0 Mn plus by M. So Emn plus by M means potential, reduction potential of the cell. Emn to E0. E0 is the standard EMF. Remember, it's a standard EMF. So when I am discussing that EMF of the cell, means I am telling about the EMF of cell. So Emn plus by M is equal to E0 Mn plus by M minus RT by NF. This is a plus 2 equation. You have already learned in plus 2 and plus 3 classes. So Emn plus by M is equal to E0 Mn plus by M minus RT by NF ln M concentration. The neutral atom has its unit concentration. But anything which is in neutral state does not change its concentration. So M concentration is equal to unity. But Mn plus concentration will vary. Depending on the question or depending on the experiment, we are using the Mn plus concentration. So Mn plus concentration will be 0.02 or 0.05 or 1 point something, whatever it will be given to you. And R is the gas constant. T is the absolute temperature, means in Kelvin scale. when any temperature in Celsius scale is given, you add 273 to make it what? To make it the whenever R is equal to gas constant, R is equal to T is temperature. So if it is in Kelvin scale, capital T is equal to in Kelvin scale. N small n is the number of moles of electron lost or gained, and capital F is the Faraday 96500 Coulomb. So RT by NF. And here T, F, all these are nearly constant. So when you put R, T, and F value, it comes to be 0.0591. So the real equation is E Mn plus by M is equal to E0 Mn plus by M minus 0.0591 by N log M concentration by Mn plus concentration. And M concentration is always 1. So you see it is written here also. And whenever you convert ln into log, then you multiply 2.303 because ln to log करने में 2.303 को multiply करना है. So if it is a ln x, then log x become your 2.303 log x. Because you remember this, that ln has been changed to log. Okay. So the equation becomes E Mn plus by M is equal to E0 Mn plus by M minus 0.059 by N log 1 by Mn plus concentration. So E cell equal to, I can simply write, because the same thing is written again, Mn plus by M. So you can write E is equal to E0 minus 0.059 because the R, value of T, value of F, all are constants. So when it is multiplied, it gives rise to it gives rise to 0.059 by N log 1 by Mn plus the concentration. This is your Nost equation. So if you put this equation to calculate the E copper 2 plus by copper or potential of the cell, for example, the cell is copper 2 plus 2E becomes copper. Then E copper 2 plus by copper is equal to E0 copper 2 plus by copper minus 0.059 by 2 log 1 by copper 2 plus concentration. 1 by copper 2 plus concentration. Copper 2 plus concentration will be given to you in the exam. It may be 0.01 or 1.11, whatever it may be. Then you put this value of copper 2 plus concentration. Calculate the log value and you can get the E0, E copper 2 plus by copper. And E0 copper 2 plus by copper value is plus 0.34 volt. It will also given to you because standard electrode potential or E0 will be given to you in the examination. And E0 copper 2 plus by copper will be also given to you. Okay, for example, take another cell that is Cr2O7 minus 72 minus plus 14H plus 6 electron become Cr plus 3 plus 7H2. In this case also, if you put the equation E Cr2 minus plus the value of N, here N is the number change in electrons. So there you have seen that when we can take 2 minutes break. Mahendra, Anil, Najrul. Yes, okay, okay. Mahendra,
Yes, sir. Yes, sir.
thank you. We can take 2 minutes break. Okay.
जी सर.
Okay.
Okay.
Okay, we'll resume again. So in this way, the Nost equation is used to calculate the EMF of the cell. Nost equation is used to calculate the EMF of a cell simply by the formula E equal to E0 cell minus RT by NF ln. Then you can have concentration of products to the power their coefficient by concentration of reactants to the power their coefficients. And this concentration of products by reactants is sometimes called as it is also called as the rate constant Kc. So you can write ln Kc. Then you can relate between the relation between E and E0 and the what? Your equilibrium constant Kc. Okay. Then you can see redox equilibrium constant. Okay, that thing I'm telling you, that whenever a reaction is written, in the reaction, remember, the concentration of product by concentration of reactant is nothing but your rate constant K. So you can put this value as rate constant K. So E cell is equal to E0 cell minus 0.0591 by N log K, where log K is your equilibrium constant, so is called your equilibrium constant. So consider, for example, you have a cell SN4 plus 2 Fe2 plus gives rise to SN2 plus 2 Fe3 plus. So here SN4 plus becomes SN2 plus, so it is a reduction, and Fe2 plus becomes Fe3 plus. It is called as the oxidation. So two reactions are given here. One is reduction and one is oxidation. Then you can write log K is equal to uh, 1 into 2 3, or K is equal to 10 to the power minus 21.3. So in this way you can solve some problems based on the Nost equation. So Nost equation is used to calculate the EM of any cell at any concentration at any temperature and pressure. Okay. Redox titration curves are, it is not so much important because it requires again graphical representation. So I'm not going to that one. Now we go to redox indicators. Now we'll discuss about redox indicators. Then what is this one? Now I'm telling you what is called redox indicators. Redox indicators. So you know a redox indicator is a compound which can undergo a redox reaction and change color depending on the potential of the solution. So remember, redox indicator is a compound which can undergo a redox reaction and change color depending on the potential of the solution. The oxidized and reduced form of the indicator have different colors. So oxidized has one color and reduced has another color. And both are in equilibrium. So I can say indicator OX1, indicator oxidized, having color X. When gains electron, it becomes indicator reduced, having color Y. So when an indicator gains electron and it changes into another indicator having different color. So color X is for the initial color Y is for the color after gain of electrons. Then for that also you can apply the Nost equation. E is equal to E0 oxidation slash reduction minus 0.0591 by N log indicator reduction by indicator oxidation. So this is also called redox indicator, and how to calculate the potential of the redox indicator. Formula, how much? What is the formula? E is equal to E0 oxidation slash reduction minus 0.0591 by N indicator log indicator reduction potential, sorry, concentration by indicator oxidation concentration. Or also you can say concentration of indicator with the reduction form is nothing but intensity of color Y. Intensity of color Y by intensity of color X. Intensity of color Y by intensity of color X. Also you can say like this. Intensity of color Y by intensity of color X. You can say in this way also. Okay. Next, we'll go to okay. Similarly, one example of indicator is ferroin, F-E-R-R-O-I-N, ferroin, and is prepared by dissolving. Ferroin is prepared by dissolving. 1 minute. Ferroin is prepared by dissolving 110 phenanthrolene and iron 2 sulfate. So 1 comma 10, position number 1 comma 10, the local positions, phenanthrolene, you are listening all? Gitanjali Pari joined. Okay. Okay. So when 110 phenanthrolene reacts with iron, iron 2, it form a complex, and that complex is called as ferroin. And ferroin is an indicator, and it is prepared by taking 3 moles of phenanthrolene and 1 mole of iron sulfate. 3:1 ratio is there. 3:1 ratio to prepare ferroin as an indicator. Then you can see diphenylamine. So it is important to mention that diphenylamine is also one of the redox indicator. So we are discussing about redox indicator. That is your diphenylamine. Diphenylamine. One minute. Diphenylamine. So that is a 2 benzene ring on both sides, and in between we have NH group. It is a colorless compound. When this compound, diphenylamine, is one of the earliest redox indicator, it is to mention, it was introduced by Noop for titration of iron 2 with potassium dichromate. The reduced form of the indicator is colorless, and the oxidized form has a deep violet color. So you see how the reduction takes place. So reduction during redox reaction, indicator plays a vital role also. Sometimes some are self-indicator because they are colored. So no need to have a colored indicator always. Looks like diphenylamine is colorless, but when it undergoes redox reaction with another substance, it is now deep violet color, diphenyl benzidimine, benzidine, diphenyl benzidine is color. Similarly, one more compound is diphenyl amine sulfonic acid. It is also color. So now I will tell you different standard indicators and their color. For example, indigo tetrasulfate is an indicator. Its color, the reduced form is colorless, but oxidized form is colored blue. Similarly, methyl blue has blue in color in oxidized form, but all have the reduced form is colorless. Then diphenylamine also colorless, violet, just I have explained you. Barium diphenylamine is also colorless in its reduced form, but violet to red in its oxidized form. Okay, then we'll go to redox titration in non-aqueous solvents. In non-aqueous means without having any water. First of all, we'll discuss about which solvents are called non-aqueous solvent. They are acetic acid, acetonitrile, then dimethyl formamide, dimethyl sulfoxide, DMSO, like this. These are called as the common non-aqueous solvents. Aqueous means water. You know water solvent very well, but non-aqueous solvents are also important. Some of them are acetic acid, acetonitrile, then you have dimethyl formamide, or called DMF, and DMSO, or dimethyl sulfoxide. So these are called as the non-aqueous solvents. Any doubt, students, about non-aqueous solvents? Hello?
Hello.
Now, can you understand what is non-aqueous solvents?
Yeah, we understood what is the difference between, but why they are known as non-aqueous solvent?
See, aqueous solvent means they have water. Aqueous means aqua means water. If there is nothing with water, acetic acid doesn't have any water. If you're taking acetic acid solution, it is not having water. Water has hydrogen bonding. Remember, water has hydrogen bonding and it has high dielectric constant of 80. Last class I have told you. Water has very high value of dielectric constant. That's why water is capable to dissolve many compounds. But non-aqueous solvents only can dissolve organic compounds. Clear?
Clear.
So organic compounds may be benzene, maybe carbon tetrachloride, but here I am discussing about DMF, dimethyl formamide, DMSO, dimethyl sulfoxide. These are all non-aqueous solvents. Okay. Then we go to application of redox titration. So one application is your oxidimetry reagents. Oxidimetry reagent means the reagent which is in aqueous solution and in acidic medium simply undergoes reduction, means it is reduced, like MnO4 minus called potassium permanganate or manganate ion, KMnO4 minus, from which it comes as MnO4 minus. So MnO4 minus in presence of acid plus 8H plus 5 electron changed into Mn2 plus. Change into Mn2 plus. It is called as the conversion of potassium permanganate into manganese ion, Mn2 plus ion. And it occurs in acidic medium. It occurs in acidic medium. So potassium permanganate is a powerful and versatile oxidizing agent, and it can be used in acidic, neutral, alkyl medium. It has specific application in different medium. In acidic medium, KMnO4 is a strong oxidizing agent as it gets reduced to Mn2 plus as per the equation. In neutral medium, MnO4 minus become MnO2. So question will come in acidic medium, MnO4 minus से क्या होता in basic medium MnO4 minus से क्या होगा in neutral medium MnO4 minus से क्या होगा. This is called as the oxidimetric reagents. They are oxidizing agents. But what will happen in different medium? Acidic medium, basic medium, and neutral medium. So remember, in acidic medium, MnO4 minus becomes Mn2 plus. But in basic medium, MnO4 minus becomes MnO2, manganese dioxide. And in basic medium, it is a neutral medium. In basic medium, it will be MnO4 minus to MnO4 2 minus. MnO4 minus to MnO4 2 minus. These things you remember which one undergo what type of reactions in different concentration of potassium concentration or in different medium. Therefore, it is the most important things. Similarly, one more is your oxalic acid along with KMNO4 reaction. It is in plus 2 practical called redox titration. Oxalic acid and KMNO4 reduction I will discuss after 1 or 2 minutes break. Okay, so students, can you take the break for 2 minutes? Hello?
Yeah, sure, sure.
Can I take a break? Yes. Mahendra, okay, very good.
Yes, sir.
Okay, thank you, thank you.
Yes, sir. Yes, sir.
Thank you. Okay, we should continue again. So next is your, this is all about your potassium permanganate, KMnO4 minus, how it undergoes in different medium. So in acidic medium, MnO4 minus becomes Mn2 plus. In basic medium, MnO4 minus becomes MnO4 2 minus. And in a neutral medium, MnO4 minus becomes MnO2. For these things, you remember it. Next one is your oxalic acid and KMnO4 titration. So oxalic acid and KMnO4 reacts in this way. C2O4 2 minus is your oxalate ion plus MnO4 minus plus 8H plus H plus gives rise to CO2 plus Mn2 plus water. Similarly, cerium 4 Cerium 4 also undergo oxidimetry titration because it can is a powerful oxidizing agent in acidic medium, and cerium fluor changes to cerium 3 plus, the oxidizing agent, and itself undergoes a reduction. If a particular element undergo reduction, it is called as a good oxidizing agent. Called good oxidizing agent. Next, potassium dichromate, K2Cr2O7 plus 14H plus 6 electron give back to Cr2Cr3 plus 7H2O. Here also E0 is equal to 1.33 volt. So same thing occurs here also. Similarly, one more oxidizing agent is potassium bromate. Potassium bromate. So like this, many reagents are there. Not going details in this. Next one is your reductimetry. Okay. Do you know what is called iodimetry? The method in which iodine is used for the determination of reductant, it is called iodimetry. But what is called reductimetry? These are iron, chromium 2, titanium 3. Because iron 3 plus become iron 2 plus, chromium 3 plus become chromium 2 plus, titanium oxide, here it is TiO2 2 plus become Ti3 plus. So these are all examples of the reductimetry reactions. That's all about your this chapter. Redox reactions. So in a summary, chemical reactions involving oxidation and reduction are called redox titration or redox reactions. And here electron transfer takes place since oxidation proceeds with loss of electron, while reduction is accompanied by gain of electron. Then what we learned here is that both the process must occur together and most components from each other. The separation of redox reactions into two components, half cell, is a suitable way of indicating species that gains electron and that loses electron. We know it. Oxidizing and reducing agents may differ among themselves in strength. For obtaining comparative value of their strength, it is essential to measure under standard experimental condition the potential difference between platinum and their solutions relative to a standard of reference. The reference electrode is called as the hydrogen electrode. Some remember always the reference electrode is always the hydrogen electrode whose potential is equal to 0. So H2H plus slash H2 E0, 2H plus slash H2 equal to 0. Means E0, 2H plus by H2 has the referent electrode whose potential is okay. So next we'll go to Uh, terminal question answers will discuss here. It calculate the potential of a for a platinum electrode immersed in a solution that is 10 to the power minus 2 molar KBr and 10 to the minus 3 molar in Br2. The electrode reaction is given below. Okay, okay. So Br2 become Br minus. So KBr means it is Br minus. So Br2 to plus 2 electron, it becomes 2 Br. Calculate the redox potential of SN4 plus SN. Oh, that is the next question. So how to solve it? I'm just solving it. Solving it in this way. Here, first of all, what you do? The potential question number 3. The potential of the at the equivalence point is given by E1 plus E2 by 2, and it does not depend on the constant. It is told that the electron potential of SN4 plus by SN system is simply E1 plus E2 by 2. Then question has come, calculate the equilibrium constant for the reaction Mn upper minus plus Fe plus F5 Fe2 plus 8H plus Mn2 plus MCH-3. So first of all, you will know which one undergo reduction, which undergo oxidation. E0 Mn upper minus to Mn2 plus is here reduction because Mn plus 7 to Mn plus 2 is a reduction. Already I have explained it. And Fe2
Huh.
plus to Fe3
Two
plus
bones
is
meet at a
oxidation.
joint. Two
Hello?
bones meet at
Okay. Anyway, so E0 Mn upper minus to Mn2 plus, it is 1.52 volt, and E0 Fe3 plus by Fe2 plus 0.77 volt. The redox reaction will be Sn2 plus 2 Ce2 plus 4 plus become Sn4 plus 2 is Ce2 plus. So it is simply by putting formula you can do it. One more question is come on Nost equation. It is E cell equal to E0 cell minus 0.0591 by N. N is the number of change in electrons log right side concentration by log left side concentration. Okay. Metric titration. 11 is what? Your complexometric titration. So here we will discuss about metal ligand. There is a reaction between metal and ligand, and hence it is called complex of titration. Metal ligand complex, metal ligand equilibrium, factors affecting stability of metal ligand complex, then principle of complexometric titration, EDTA, and important chelating agent, then EDTA titration and pH, effect of other complexing agent, metal EDTA titration curve. These are some of the things we'll discuss one by one. First of all, common sense, remember that complexometric titration means Rayleigh formation of complex. And complex is formed between metal and ligand. Ligand has a valency electron, means a pair of lone pair it will have, and metal is deficient of electron. So metal orbitals are deficient, and the compounds which are coming to attach, they are ligands having lone pair of electron called sufficient. Where metal and ligand forms bond, it is called metal ligand bond, or called a complex. So first of all, we'll go to review of coordination compound. So it definitely is a topic in plus 2 science. Coordination compound, very important one. You know also Werner's coordination theory. Werner says derived a coordination theory based on which the structure of many complex compounds have been established. And here I will discuss about metal ligand complex. Okay. Formed when and any ligand having lone pair of electron donate electron to metal. So when metal ligand, so what is ligand? Ligand is a species having a lone pair of electron or a negative charge, capable of donating its electron pair to the metal.
1, 3. 7 or 9.
Hello. These are all ligands.
Yes,
So
yes.
ligands must have a pair of electron to donate to metal atom, and metal must have vacant orbital to accommodate this pair of electron. Hence, metal ligand bond is a coordinate covalent bond, where ligand is the donor and metal is the acceptor. Any doubt? Ask me. Any doubt? Coordination compound, any doubt? Ask me. Metal ligand bond, how it is formed? Okay. So now I will give you one example of a complex formation. For example, you have taken a copper solution, copper 2 plus ion is your copper solution, copper ion, and you add ammonia. Copper ion and ammonia, they will react. Means not react, actually, it forms a bond around copper. So ammonia has a lone pair of electron. Ammonia has a lone pair of electron. Ammonia donates electron to copper. When ammonia donates electron to copper, then it forms a tetraamine copper complex. Tetraamine copper complex, CuNH3 whole 4 2 plus. It is called tetraamine copper complex. CuNH3 whole 4 2 plus. Tetraamine copper. It is a blue color solution, deep blue color complex. Russian blue also called. So here ammonia is the ligand and copper 2 plus is the metal ion which can accept these ligands. Similarly, metal carbonyl, iron along with carbon monoxide forms FeCO5. It is called a metal carbonyl. Fe plus CO gives you FeCO5. It is called metal carbonyl. Then now, what is a ligand? The charged or neutral species with a lone pair of electron that form the coordinate bond with central ion is called as a ligand. Direct question will students come. What is ligand? What is a complex? What is a coordination sphere? What is coordination number? All these things will come from this topic. So ligand means any species having a tendency to donate a pair of lone pair of electron to central metal atom or ion. It is called as a ligand. There are many ligands. I've told you water is a ligand, ammonia is a ligand, amines are ligands because they have lone pair of electron. These are ligands. But they can donate electron pair to the central metal atom. So larger molecules like one more thing, ethylene diamine, ethylene diamine is your bidentate ligand, ethylene diamine. So these are all similarly if it is OH minus, NH minus, these are NH2 minus. These are all called as the unidentate ligands because they have only one donor side. So students, can I take some water? Okay. So a ligand can be unidentate ligand, a ligand can be bidentate, a ligand can be polydentate. If any ligand like EDTA, ethylene diamine tetraacetic acid, is a hexadentate ligand. It has 6 donor sites. So it can form one EDTA can form 6 number of coordinate covalent bonds because one is EDTA, ethylene diamine tetraacetate. So if you remember the donor sites, if the number of donor sites equal to 2, it is called bidentate. If it is 3, it is called tridentate. If it is 4, it is called like this. If it is 1, it is called unidentate ligand. Depending on the denticity, the compound is formed. For example, EDTA is there, only one EDTA is sufficient to form a complex. But if OH minus is there or OH is there, it takes 6 ligands at least to form octahedral complex. So EDTA, you can see the book also, figure 11.1, it is given EDTA, NH, then CH2, then CH, then NH. NH has not done anything else directly, that has to COO minus. So one is COOH, one is what? COO minus. Then some ligands are called ambidentate ligand, means they can coordinate on both sides, like NO2, ONO, nitro, nitrito. They have same formula, that is N1N and 2 oxygen, but one is different property, NO2, other one is different property, it is ONO. So one is nitro, one is nitrito. Similarly, our other two are CN minus and NC minus, cyanide and isocyanide. Similarly, one more is nitro and nitrito. One more is it is called as CN, NC, NCCN, NO2, ONO, and one more SCN, NSC. SCN is thiocyanate and NSC is isothiocyanate. So in this way, you classified the ligands into bidentate, tridentate. Then again, we have classified ligands into simple ligands, complex ligand. Similarly, it can be also classified what is called ambidentate ligands. Now, chelates. Do you know if any ligand has a tendency to donate 2 electron pair to a central atom, and these 2 atoms are on opposite side of the molecule, then it can form a cyclic structure. This is called chelates. So chelates means when a polydentate ligand simultaneously form more than one bond with same metal atom, it will be a ring type structures and called a chelate. The complexing agent is 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 called as a complexing agent. Or EDTA is a good example of cleansing or cleansing. Good example of good example of cleansing reagent. It is called chelate ligands. So EDTA is a important chelating agent. EDTA. Similarly, one more thing, stability of the complex can be known from different types of ligands attached to it. And this is also very important thing. You should remember that EDTA is a good reducing agent, but before it was an oxidizing agent. Next, estimation based on redox and complexation equilibrium system. Then metal ligand equilibrium. Metal is copper, example, metal is copper 2 plus, and non-metal is what? Your equilibrium, nitro group or any group. So when copper cadmium 2 plus reacts with ammonia, it forms cadmium tetraamine 2 plus, means it is a square plural complex. So accordingly, equilibrium constant K can be calculated. Once you calculate K or Ka, whatever it may be, K or Ka, then we can put the bile will process. Then you can say that the equilibrium constant is also related to the concentration term. And one more is called cumulative formation constant or stepwise formation constant. It is simply if a reaction takes place in 10 steps, and each step you have a kinetics K1 into K1, K2, K3, then you can say the overall equilibrium constant or cumulative equilibrium constant is K1 into K2 into K3 into K4 like this. And K1, K2, K3, K4, you have the photograph of it. Similarly, AgCl plus Cl minus gives rise to AgCl2 minus. AgCl gives rise to Ag plus Cl minus. Depending on the reaction, you can able to predict the EMF of the cell. Factor affecting stability of metal ligand complex. Factors affecting stability of metal ligand complex. Nature of the metal ion, then nature of the ligand, basicity of the ligand, size of the chelate ring, number of metal chelate ring, resonance effect, allosteric effect. These are some of the factors affecting stability of metal ligand complex. We will discuss one by one. Students, break for a minute. I'll take some water. Okay.
Yes, sir. Yes.
Yes, sir.
Okay. complex. First one is the nature of the metal ion. The nature of the metal ion determines the type of bonding with the ligand donatum. Smaller the ion with a higher charge lead to stronger complex. Smaller ion with a higher charge. For example, Fe2 plus and Fe3 plus. So it will be Fe3 plus will form stronger ligand. Similarly, smaller ion with higher charge will form stronger ligand. Next one is nature of ligand. For example, the ligands forming chelate are more stable. For example, a chelate ligand, ethylene diamine form chelate ligand. So a ligand which forms chelate complexes are more stable as compared to ligands which are immodented or bident, maybe or not forming any ring compounds. If a ligand forms a ring compound along with metal, it calls a stable complex. Size of chelate ring. You know that 5 and 6 member rings are more stable. So maximum stability is for 5 and 6 member rings. Then the stability of the complex is directly related to the number of chelate rings formed between the ligand and the metal ion. Greater the number of such rings, greater is the stability. Then next one is resonance effect. The formation of 5 or 6 member ring can be explained in terms of the conjugative effect, which is the stability of the complex. Then next one is last one is steric effect. The steric effect refers to size of the ligand, their spatial arrangement, and the distance between the uh, coordination site. These all Any doubts you can ask me, students. So coordination compound is very important because many of the chemical reactions are complex reactions, and complex reactions are somewhat bonding between metal and ligand. And in pharmaceutical industry, in rubber industry, many petrochemical industry also you see this concept. Any doubt you can ask me. 7 minutes left, you can ask me the doubts. Strong ligands, and also you can ask me the electrochemical cells are very important in battery industry, in car factory industry, or in terms of the industry of called as industrial industrial solutions where it is prepared. Many batteries like primary cell, secondary cell, there you find electrochemistry and important implications. Electrochemical cells, reduction oxidation cells. So no doubt from any side. Good.
Sir,
Any
am
doubt
I
or
audible? Hello.
yes, you're audible. Tell me.
Sir, I want to ask what type of question basically come from this chapter? Can you explain?
Yes. Good thing you have asked me. Basically the question will come from that what is an electrochemical cell, then write some redox reactions, how to calculate potential of electrochemical cell, E cell equal E0 cell equal to E0 cathode minus E0 anode. So value will be given to you. E0 copper 2 plus by copper is 0.34 volt. E0 zinc 2 plus by zinc is minus 0.76 volt. Calculate E0 cell. Very simple. E0 cell equal to E0 cathode minus E0 anode. You can use Nost equation, that is E cell equal to E0 cell minus 0.0591 by N log concentration of metal by concentration of ion. Their metal ion concentration will be given to you. You have to calculate E cell. These questions will come. Then also question will come that electrochemical. Then your question will come which reactions are oxidation, which are reductions. So redox reactions, simple redox reactions and electrochemical cell. Question will definitely come from that. Then how to calculate the potential of a cell, which one is best reducing agent. I've told you negative value of E0 means good reducing agent, positive value of E0 means good oxidizing agent. The electrochemical series, the table I've explained, the table where E0 cells are given, that thing you have to slightly remember. Not so much, but only an idea that which one is negative value, which one is positive value. From that you can say, okay, which one is reducing, which is oxidizing. Like
Thank you, sir. Thank you.
can I take class on Saturday or not?
Yes, sir. Yes, sir.
Now, can it possible to take class on Saturday?
Yes.
Others have to tell, otherwise it becomes a problem for me. Because Saturday is a,
Yes, sir.
I
Yes.
can take class on Saturday.
Yes, sir. Yes.
Because then Monday, Tuesday, Saturday and Sunday, if you take two classes, then no need to do class on Monday and Tuesday. That is my request.
I will prefer to have classes on Saturday and Sunday rather than on working days.
Yes, yes, because I think you are all employee in some
Yeah,
of the institutes or somewhere else you are working.
correct,
So, no,
correct.
so it is possible to take. Can I take this class on this 2 day or any problem for the IGNO center? This is most important thing. If you are agree, then I can take the class
Yes,
on
sir. Yes,
Saturday
sir. We
and
are free, sir.
Yes, you can
Or
take,
we
sir.
are ready to take class.
okay. On which time? Same time.
Yes, we'll
Yes,
go
sir.
with
Same
same
time.
time, sir.
Okay. So then I can tomorrow I will talk to because if anyone will left out, then it will be the biggest problem for me. All have to join at least.
Yeah.
No, definitely we will join, but I will request all attendees to if we can shift it in afternoon time because evening time is basically a family time. So if I request if we can do we can have classes in afternoon or maybe morning time will be better.
Sir, it is impossible in the afternoon. Yeah, class
Class timing
timings.
will be same.
Better to have the
Only I
class.
want to take
Yes, better to have
same.
the class in the evening session itself,
Yes.
sir.
Yes, sir. It is no,
Sir, 2 day we can manage
Because
it,
as
sir.
see students. It is on the evening session only. But I want the class to be taken on Saturday and Sunday. The remaining two classes.
Yes,
No,
sir.
no,
Yes, sir. We can
two
manage.
class, no problem. Saturday and Sunday I will take the class. Then there is no class on Monday, Tuesday. That's all I want to say.
yeah, it's okay, sir.
Okay, then tomorrow class there will be same time at same class time, and tomorrow I will convey you. I'm discussing with regional center.
Yeah,
Today,
definitely,
tomorrow
sir.
at same time, the class will open. Thank you very much. Thank you.
Okay,
You
Thank you,
can
sir.
sir.
leave now.
Sir,
Thank you,
one
sir.
more thing.
Thank
Tomorrow,
you
which
very
chapter?
much.
Thank you,
Thank you.
sir. Thank you, sir.
Yes, yes, yes. Tell Rajan.
Yeah, tomorrow, which chapter?
Someone wants to say something. Yes.
Yeah, tomorrow, which chapter?
Tomorrow at
Yeah,
same
tomorrow, which
timing.
chapter you will be taking?
Tomorrow this block four, something remaining on block four. Then we'll go to block five. Okay,
Block 4, block 5. Okay. Okay.
block four. No, block four. Tomorrow will be block four because one unit is not completed. It was some portions are remaining. So block four tomorrow I will continue. If possible, then go to tomorrow block five.
Okay.
Okay. Thank you very much.
Thank you.